Hello, everyone. Today we'll be hearing about writing systems and number systems from Adam Hesterberg, also known as Pesto, a name he got working at Math Camp, where there's a constructed language called Food Tongue, where every word's the name of food, hence the name. While in high school, he did well in the International Linguistics Olympiad, and ever since then has been coaching the US team. Right now, he's the Assistant Director of Undergraduate Studies in the Computer Science Department here at Harvard. He lives with his cat Artemis and a few roommates in an apartment. I guess not here in Cambridge because I'm not in Cambridge, but in Cambridge. Please welcome Pesto.
Hello. For meeting today, I'm going to tell you about all of the number systems in the world and all of the writing systems in the world. This won't be a very in-depth talk since this meeting is supposed to be, an hour? And there are a lot of languages and number systems and writing systems. But actually, there aren't really so many, so we'll be able to, in some sense, get through all of them. Let's start with number systems. So there are lots of different ways that human languages do number systems, but they don't differ that much. In particular, we can make a first division of number systems into number systems that can specify large numbers. So have ways of saying the number 101 and have it be different from 102, and ones that can't. For instance, there is a language with words for 0, 1, 2, 3, and 4, but beyond that, anything you say is many. That incidentally is a language from which I get my name, Pesto. Or to use real human languages as an example, there is a language, Pidahap, spoken in South America with words for one and few and many, but they don't distinguish, say, 100 from 101. There's even a language with words for 1 through 34, and then many. So those are a few sporadic languages. There are a few other slightly different systems, but all something along those lines. Number systems that can specify large numbers precisely are all base systems. So base systems as in there is some value like 10 such that your way of forming numbers roughly repeats every 10, or where multiplying by powers of the base leaves you with numbers that you express in basically the same way. Like English uses base 10 because we humans have 10 fingers, and many languages use 10 for that reason. There aren't even many bases used by human number systems. So besides base 10, there are number systems that use base 20 because we have 10 fingers and then 10 fingers again. Or base 5 because we have 5 fingers. Or base 4 because we have 4 fingers. Who needs a thumb? Or base 8 because we have 8 fingers. Or base 6 because we have 5 fingers and a fist. Or base 12 because we have 10 fingers and 2 fists. And I believe that is every base that is used by more than one number system in the world. There are also a few weird bases used by exactly one number system, like 60 is the base used by Babylonian. So everything is a base system, uses a base that is just our number of fingers, roughly. And then occasionally there are a few weird things. In computer science, you might have to think about whether your representations of numbers are big endian or little endian, whether you start with the biggest things and work your way down, or start with the units digit and work your way up. But every human number system is big endian, roughly. You start with the biggest digit. Except sometimes there are just a few transpositions. For instance, in English, we say 13, 3 plus 10, instead of 10 plus 3, even though roughly we go from largest to smallest. About the weirdest it gets in this respect is German, where the number, say, 123,456 would be said in this order: 123,456. But other than small transpositions like that, languages all go from biggest to smallest in number systems. Also, sometimes if you've watched some number ticking up, like a car odometer, sometimes when you are close to a nice round number, you are excited about it and start counting down your time until you hit the round number, and humans do the same thing. So sometimes languages count down from round numbers. In Latin, for instance, you basically count up, but say 79 is un de octoginta. 80 is a nice round number. Octoginta is 80. This is 1 less than 80. And similarly, when you are close to other round numbers. I think French does something similar. This is reasonably common. Other things that human number systems sometimes do. So sometimes twice the base is special, or 2 times powers of the base. For instance, in the Gettysburg Address, Lincoln said 407 years ago. English, you might have heard, is a base 10 language, but this is a poetic, well, currently poetic way of saying 87, 4 times 20 plus 7. Even though English is mostly base 10, we used to count roughly by 20s. And incidentally, this is why numbers up to 19 are weird before we get to the regular system. So numbers up to 19 are weird in the order that we say them, 13, 14, ... And that bit of weirdness survived because we were using them so much on our way counting up to a score. And even though we no longer group our numbers by scores and, I don't know, say 4 and 17, we still have weirdness up to a score. So even if the base is not 10, twice powers of the base are sometimes treated differently. And similarly, a half times powers of the base are sometimes special. For instance, Latin is base 10, but it has Roman numerals. Not just for 1, 10, 100, and 1,000, but also for 5, 50, and 500. I guess I'm cheating a little in this example because this is just about how Latin rates its numbers, not how the spoken language number system works. But this is the example I have handy. So these few quirks of language are about all of the weirdnesses of human number systems that occur in more than one language, more than one human number system. That is, every human language that can specify large numbers precisely is a base system with one of a small number of bases based on fingers that goes biggest to smallest, except for small transpositions, sometimes counts down from round numbers, and sometimes has half or twice powers of the base be treated differently. Or is doing something specific to one language, and even that is pretty rare. So we're only a quarter of the way into the meeting, and I've gone through all human number systems.
I have a question about special numbers.
Mm-hmm.
So like when you're counting up at a certain point, it gets regular, like the teens are all named teen, but up to 10, they're all different. And then I know in French, they're all different until 16, and Spanish, they're all different until 15, Serbian 10.
Mm-hmm.
Yeah, so like, how does that?
So there is a general phenomenon that words that are used more frequently are more likely to be irregular, perhaps because words that are used less frequently you won't remember the irregularities of, and so they'll just drift toward the regular pattern over time, or perhaps because for communication efficiency it's extra important to have them be efficiently sayable. I don't think that explanation is actually true, but as a scientist who does some information theory, I like that one. For the numbers 1 through 19, this is a plausible explanation because 1 through 19 were used substantially more frequently than numbers bigger than that, because if you count by scores, then the thing that comes after the score is 1 through 19. And even when there isn't such a clean cutoff, small numbers are used more often. Like empirically, in human language, the relative frequency with which the number I is used is proportional to 1 over log I, if I remember correctly. I might have that formula wrong, but you can derive it by observing the frequencies of first digits of numbers in, say, newspapers and such, where numbers with first digit 1 come up substantially more often than numbers with first digit 2, which come up more often than numbers with first digit 3, and so on, in frequencies that are proportional to I think it's actually log of I over I plus 1 yeah, that would make sense. Like roughly log 2 of fraction of numbers that say you see in newspapers start with 1. Any other questions about number systems? Great. And there will be a test at the end. Not really, but after I talk about rating systems, we will come back to this by showing an IOL problem on number systems. It's a human language. Everything it does, like all human language number systems, that's special is specified on these 2 pages. And yet, at the IOL, with at most 1 or 2 exceptions, everyone who solved that problem got at least a silver medal, and everyone who didn't got at most bronze. This small summary is useful. Okay, let's switch gears and talk about every human rating system. So here it is a bit less cheating to say that I'm going to talk about every human rating system, because rating has only been independently invented about 4 times. Independently as in invented by people who hadn't seen some other rating system and gotten ideas from it. And if you invent a rating system by seeing other rating systems and getting ideas from them, then your writing system will look a lot like what you're copying from. So early rating systems, where by early I mean when independently invented, are logographic. That is, you have 1 character per and if you want a new word, you need to invent or remember a new character. For instance, the Chinese rating system was originally and still basically is this, or the oldest form of Egyptian hieroglyphs. Were logographic. Each hieroglyph represented 1 word, although the hieroglyphs that you see on Egyptian monuments are no longer this. So this is a sad way to have a rating system, in that if you have to learn 1 character per word and your vocabulary has some 5-digit number of words in it, then you need to learn a 5-digit number of characters. Not coincidentally, in Egypt and ancient China, there were people whose entire job it was in life to be able to read and write. So someone entered the waiting room. So the first great advancement in writing systems is that you don't need 1 character per word. Words have something in common, namely syllables. And if you have a reasonably small set of syllables, you don't need 1 character per word. You can just have 1 character per syllable, and then combine those syllables into words. And depending on your language, you might have only a few dozen distinct syllables and only need to learn a few dozen characters. or you might have several thousand distinct syllables like in English, and so that would still be a lot of characters to have to remember. But certainly fewer than you have to remember for a logographic writing system. And well, maybe it takes more characters to write out whatever you want to write out, because some words have multiple syllables. But if the characters can be simpler to compensate, then maybe you don't need as much space. Some examples of syllabaries are hiragana and katakana, two Japanese writing systems, and there are a few more. This might still be a lot of syllables to have to remember characters for, a lot of characters to have to remember. So the next great advancement in writing systems is that syllables have something in common. So you could just have an alphabet with one character per phoneme. And then instead of learning as many characters as there are syllables in language, you only have to learn as many characters as there are phonemes. And even the most phonemically rich languages, there are some West African languages, I think, that have on the order of 100 phonemes. But that's still pretty small relative to the number of syllables in a language. So fewer characters to remember, but basically the same advancement has led to syllabaries. Words have something in common, namely syllables. Syllables have something, namely phonemes. So instead of remembering a character per syllable, you can remember fewer characters, one per phoneme. As a side note, belonging somewhere in between these are abjads and abogidas, where you have one character per consonant and either leave out the vowels entirely or have vowels be possibly optional special diacritics. You think of these as having one character per consonant. And hieroglyphs developed pretty quickly to the point of being roughly that, roughly having one per consonant, plus some holdovers from when there was one hieroglyph per word, like hieroglyphs that represent sequences of 3 consonants. And English is descended from this. So from old hieroglyphs, you went through some writing system where there was a character for the consonant a glottal stop, and then a character for the consonant b, and then a character for g, and then a character for d, and then a character for, I forget what came after that. And this was used by Phoenician traders, and when the Greeks heard about this, and the Phoenicians said the first character is the sound ah, the Greeks said, oh, I get that. That's the vowel sound, ah. And so we got an alphabet. So we have languages with one character per word. Words have something in common, namely syllables. So we have languages with writing systems with one character per syllable. Syllables have something in common, namely phonemes. So we have languages with one character per phoneme. The next great advancement in writing systems is the same as the first two. So phonemes have something in common, namely features. For instance, the sounds F and V, F and V, differ only in whether your vocal cords are vibrating when you say them. That's the same as the difference for P and B, or the difference between S and Z, or the difference between T and D. And so instead of having one character for each of these, you could have one character for being voiceless, different character for being voiced. Similarly, the only difference between these top four things and their counterparts below is that you articulate the top four by obstructing airflow on your lips, roughly. Whereas to articulate the bottom four, you obstruct airflow roughly on the alveolar ridge behind your teeth. And finally, for some of these, you don't obstruct airflow completely. You let the friction of air flowing past your lips make the sound. And for some, you stop the airflow completely. So instead of having, say, 8 distinct characters for these 8 sounds, 8 phonemes, we could have gotten by just having a character for voiceless or voiced, a character for what place of articulation, a character for how you articulate, like fricative or stop. And then you could combine those features into the phonemes, and then those phonemes into syllables, and those syllables into words. So there is only one rating system in an actual human language that does some of this. So that's the Korean rating system, transliterated into English as this with or without the E, where there are pieces of characters that mean something like voiced and voiceless, and pieces of characters that mean something like fricative and stop. And you combine them into characters for phonemes, which are displayed nicely in Hangul because they're all connected pieces, roughly. And then you combine those phonemes into syllables, which is transparent in Hangul because the characters that are part of a syllable are grouped in a block somehow. It would be as if in English we wrote the syllable han like that, hung, and the syllable gul like, say, that or something. And then combine those into words with spaces between words. So in Hangul, you can see all of these levels of features combining into phonemes, phonemes combining into syllables, and syllables combining into words, all without even knowing the writing system. So if you are looking to learn one writing system as fast as possible, pick Hangul. It's the easiest one to learn because it has the most of these patterns. Or if you're looking to learn one writing system and have it take as long as possible, then, well, here are your options. This isn't to say that these writing systems are worse. For instance, the fact that the Chinese writing system has one character per word means that many distinct languages can be written using the same writing system. And in fact, this is useful in China, where many distinct languages get all called Chinese, and this works better for that the writing system can be basically the same for all of them. And languages with relatively few syllables can maybe be more efficient by having just one character per syllable and not writing twice as many characters. But anyway, Hangul is the best. Any questions about writing systems? Okay, hearing no questions, let's look at an example logic puzzle on number systems. So this is a problem from the International Linguistics Olympiad. People who solved it were almost exactly the people who got at least silver medals. So let's look at it, see if we can solve it, and claim some bragging rights. I will put a link to this in Zoom chat in case you want to, look at it on your own computer. And let's take some time to look at it individually. Okay, let's talk about how to solve this. I haven't given you enough time to solve it for yourself. At the competition, you would have had what, an hour and 12 minutes per problem, and you've been working for 5. But for the sake of having time to talk about how to solve this problem during this meeting, I'm going to talk about it now. If you strongly object to hearing spoilers, feel free to mute yourself or something. Or I guess quick straw poll first, if you would rather not hear the solution and discussion about how to solve it until you've had more time to think about it for yourself. React no. And if you want to hear solution and discussion about how to solve now, react yes. Okay, so I have the words in DOM written again here. And back to where we were talking about numbers. This is hopefully a number system that can specify large numbers precisely because, well, we're given numbers like 81 and 100, and if this language can't specify them, then I don't know what we're even doing. So this is a base system, and it's probably one of those bases. So if we want to figure out what's going on, we'd want to figure out what base it's in, and that means we probably want to know what these numbers look like in those bases. And then there'll be a few small things that we maybe have to deal with, but step 1 is just see what those bases are. So in base 10, well, we can write out the squares. Here, there they are. How about base 4? What are the squares in base 4? 1, 1, 0. 9 is 2 times 4 plus 1. 16.
Oh, we can't see what you're writing right now.
Okay, can you see me now?
Yep, that works.
Yep.
Great. So anyway, here are the numbers from the problem written out again. And here, to start with, this is a number system that can specify precise large numbers, so it's a base system. It should have one of those bases, and we'd like to figure out which. So base 10 has squares that you've probably seen before. We could write out these squares in other bases too. Like in base 4, 16 is 1 times 4 squared plus 0 times 4 plus 0. And 25 is 1 times 4 squared plus 2 times 4 plus 1. And 36 is 2 times 4 squared plus 1 times 4 plus 0. And I'll just finish writing these out. So there are the squares in base 4. And, well, these maybe don't look so much like these numbers. For instance, they seem to have lots of last digits. Whereas in base 4, there are only 2 last digits. So to save some time, let's skip 5 and try writing out 6. Those are the squares of the numbers from 1 through 10 written out in base 6. For instance, 81 is 2 times 6 squared plus 1 times 6 plus 3. And maybe on the contest you would have had to try a few more bases before you got to this one. But this one seems to look a lot like this. Now, what do I mean by look a lot like this? This is a lot of text. How are you going to compare whether this looks a lot like this? Well, a few ways you might do it. One way you might do it is to look at the last digits, like the number of times the last digit is 1 here is 1, 2, 3. And the number of times the last digit is 3 is 2. The number of times the last digit is 4 is 4. And the number of times the last digit is 0 is 1. And similarly over here, there are 1, 2, 3 things with last digit sas and 2 things with last digit ithin and 4 things with last digit thonith and 1 thing with last digit nif. So this isn't just the distribution 3, 2, 4, 1 matching. It even has the right number. Even before that, it has the right number of distinct last digits. Whereas if you write out the squares in base 5 or 8 or 20, there's some different number of last digits. So anyway, we've written out the bases. Maybe if you were at the contest, you would have to try more of them, but base 6 or actually base 12 works just as well at this step. You get the right distribution of last digits. And well, let's just try this. So if these do in fact match, if sas is last digit 1, sas means 1, thonith is 4, ithin is 3, and nif, well, this is one word, but this is, this whole thing is the number with last digit 0, then this whole thing, nif, would have to be 36, or 100 in base 6. Does this make sense? Well, we have one number that is just sas, 1, that's a square, so that's a good sign. We have one number that is just thonith, 4, that's a square, so that's a good sign. We have no number that is just ithin, and 3 alone isn't a square. So that's a good sign. How about the next biggest square in base 6? So we have 1 and 4. How about 1, 3? Well, there are 2 numbers that end in ithin, one of them short and one of them long. So if this is the base, 6, this word abo that appears everywhere is just plus, then that's nice. For instance, mer abo ithin also occurs at the end of the long number that ends with a 3. And 81 is 213, also ends with 13. So then nif thef would be 2 times 36. And well, that's nice because we thought that nif was 36. So here, twice the power of the base is maybe special in that 2 times 36 is nif thef. So just write thef after it to multiply by 2. but going up one. This is 6 times 2 plus 4 is 16. So for some reason to multiply by 2 in the 6's place, you use an on, and to multiply by 2 in the 36's place, you don't. What else is allowed to be weird about number systems? So we started with the biggest digit. We have that twice the power of the base is a little bit special. How about half powers of the base? So how about, what's next? 25 is 4, 1. So this one at the bottom ends in something plus 6 plus 1. If Tondor were 18, then this would be 25. That is, Tondor is half a power of the base, is 36 over 2, and it gets its own word. And conveniently, since this is base 6, we can get all of the multiples of 6 just by combining a 6, 6 times 2, 6 times 3, 6 times 3 plus 6. If we wanted 30, we would need to combine Tondor with Meranthef, Tondor Abo Meranthef. And then you're up to 36 and a new word. Okay, so the roadmap for things that human languages can do that are weird was enough to get started on this problem. Just write out all of the numbers we wanted to find in various spaces and see which one matched. Questions about this or number systems or the IOL or anything?
I mean, that wouldn't like always work because, you know, the transpositions or things like that, you might not like, how would you know when you're looking at it to be like, okay, I can try out the distributions versus not.
Right, I cheated here a bit by assuming that there would be no transpositions meddling with looking at the last character and matching them with the last characters of what we wanted. And if there had been such transpositions, then this might not have worked and you'd have wasted some time on this and then had to try something else to match things up if there were transpositions. Like one thing that wouldn't have worked nicely here, but would have worked nicely if you were doing some language with transpositions, but not so many different ways to write its 6's digit, would be to look at lengths of numbers. Like here are some short numbers. Maybe those are the smallest numbers and 100. And here's a big number. Maybe that means it had lots of digits, and try to match things up that way. If you tried to do that for this problem, you would waste some time because like this string is long, but it corresponds to a number with not many digits. It's just what, or say this string is long, but it corresponds to a number with not many digits. Maybe you would be able to do the matching anyway, but maybe that approach would fail and you would spend some time on it and then try a different one, like the last digits. But I skipped the step of some false starts for time's sake. Good question.
What is the frequency of like different kinds of base systems which show up?
Yeah. An overwhelming majority of human-based systems are base 10. Of base systems that are not base 10, most of them are base 20. These other bases that appear more than once but not many times mostly appear specifically in Papua New Guinea or near there, Southeast Asia. Papua New Guinean languages have a thing for, are known for having a variety of bases. Yeah, so I don't know offhand what fraction of human languages use base 10 and base 20 and the others, but almost all 10 of the remainder, mostly 20.
You listed out the writing systems. Which ones are the ones that are, or like a few writing examples of writing systems? Which ones were the ones that developed? You said there were 4 that developed independently. Which 4 were they?
Right. So besides Chinese and the Chinese writing system and Egyptian hieroglyphs, I don't remember whether we know exactly which writing systems developed independently, and even if we, the human race, knows, I don't. But I think that writing developed independently in Babylonia once, and I think that it developed independently in the New World. I guess it must have developed in the New World because there was writing in the New World before contact with the Old World. Was that originally a Mayan writing system? Well, at least one independent development in the New World. So the set of roughly 4 is probably roughly those. Once writing was developed, it generally spread pretty quickly. So places that might have invented it independently didn't need to because they could just copy it right away. Okay, well, if you want to try solving logic puzzles with number systems for yourself, if you Google North American Computational Linguistics Olympiad or US Linguistics Olympiad number system problems or past problems, excuse me, and look for problems that say they're about number systems, you can find problems like this one, often ones that don't require you to write out a whole bunch of different bases because one of the more common ones will work. And so you could try such logic puzzles for yourself. That's all I have to talk about today. Thanks for inviting me.
Thanks for talking.
Thank you. That was really interesting.
There's also writing system puzzles that you can find too.
Oh yeah.
And they also like they'll often be like those on that list somewhere.
Mhm.
But they're often like, the ones that are hard for me are the Southeast Asian ones, which are sort of complicated.
Knowing that a rating system is, say, either logographic or a syllabary or an alphabet or an abjad or an abugida helps substantially less with trying to solve one of these logic puzzles than knowing that a rating system is basically write out numbers in base either 4, 5, 6, 8, 10, 12, or 20. So there is more variety and problems to solve about rating systems on the NACLO. Cheerio.
Thanks everybody for coming, and thanks Pesto.